Okay, so Colloquium from CIM and CMUC. Bandeira. He has a long history with the department. So he was here since high school when he was in the Projeto Delphi for 3 years. I was still. He then did his undergraduate master studies here. He went on to Princeton for a PhD in applied and computational mathematics. He has been a postdoc at MIT, associate professor at Courant, and is now a full professor since November, I think.
September, but yeah, close enough.
Well, okay. So he has received an Isaac Award for Young Scientists, a STEM Research Fellowship. He has published more than 20 papers in the last 2 years on top optimization journals. So he's one of the new rising voices in optimization. So it's a great honor to have Afonso speaking for us today. So thank you very much.
Yeah, thanks so much. Thanks so much for the introduction, and thanks so much for all of you for coming. And I must first start by apologizing that for not being there in person. But, you know, with the new outbreak, there's been quite a few cases here, some of which in the university, and I didn't want to risk being a vector for this into Coimbra. And so, thank you very much for being part of this experiment of trying to do this virtually. And incidentally, here in the university, there's a big initiative to start doing more of this because of our carbon footprint. So actually I had like a lot of support from the university to set up all the system and so on. So we tested a lot. I hope this works. This works well. But you know, I can't see your faces as well, so it's harder to see if I'm saying something, I'm going too fast, too slow. So please stop me if something is not clear. If someone raises their hand, I can see it. So please stop me if anything is not clear at all. Okay, now I mean, I should also say that it's of course a great pleasure to go back to Coimbra, even if only through a video call. Right? This is where I learned most of the math I know. I spent many years there as a high school student training for Olympiads. My undergraduate, my master's, in fact, a lot of time in that particular room. Just 10 years ago, I was still a master's student there in Coimbra, and most of the math I know it's to Coimbra for sure. And yeah, it would be very nice to see a lot of you again in person. This time, I guess we'll have to be the video call, but I'll visit in person soon, I'm hoping. Okay, so I'll move to the more technical side of the talk, the actual talk. So I'll talk about, I decided to give sort of a more broad audience talk about what interests me and the type of research that I've been interested in. I will, especially being on video, it's quite hard to manage time properly. So I try to prepare it for a bit less time so that it gives me a bit of time to show maybe one of the two things a bit deeper on the board. So depending how much time we have in the end, I'll do this. And the things that I do, very, very broadly defined. We call it in our community the mathematics of data science. So mathematics behind understanding what can we learn from data, how can we learn it, what are bottlenecks, and so on. And so I used to start presentations by showing statistics of how many clicks are there on Google, or how many queries are there on Google per second, or how many people are on Facebook, things like this. I think by now no one's impressed by this anymore. Everyone knows that these numbers are just ridiculously big. So instead I decided to look into other statistics that even I thought were interesting when I was preparing this talk. So one of which is, can you now see the slides, just to make sure? Yeah. Okay. So this was an article in The Economist recently, or somewhat recently, saying that the world's most valuable resource is no longer oil but data, right? And that there's many huge companies that they live, they're basically almost natural resources company. The resource is just not natural. The resource is data. Right, and they're basically data companies, right? You go online, they're learning about you, they're learning about the world, and then they are able to monetize this. Right? And this is a huge resource. In particular, I also came across, as I was looking into things to prepare for this talk, came across into a report by McKinsey, one of the big consulting companies, that they estimate that in the next decade, AI-powered applications, just another word for sort of data, like data, things that use data, it will add $13 trillion to the global economy. So, you know, when I read this, I wasn't quite sure what this meant. So I went to see how big the global economy was. And the global economy is maybe like 80 or 90, right? So we're talking about something like a 15% increase on the size of the annual global economy, right? This is a potential huge impact, right? Comparable probably with actual oil and the impact it did have. And I found this cartoon that I thought was quite good. So you see someone being auctioned for their data, right? And one thing that I try to look for is what's the estimated value of one's data? Like how much is your data worth if you were actually able to sell it to a company? And from what I look, these numbers that you see here are actually quite underestimated, probably by a factor of 5 or 10. But it's hard to know because it's very hard to put a price tag on these. Okay, so I will tell you a bit about, in general, about how I think about these problems, but I want to give you a specific instance that's maybe not as related to, you know, the social side of data, but a different kind of problem. But the type of mathematical tools are very, very similar. And it is definitely a big data type of problem. And this is one that's sort of some sentimental value to me because I did my PhD in a group that was sort of obsessed with this problem. The people around me during my PhD, this is the problem they cared about. And so I ended up, a lot of the math that I developed during my PhD was motivated by problems that my colleagues were having as they were trying to solve this. So this is known as Cryo-Electron Microscopy. So this is a form of imaging. And it's a form of imaging where you sort of spend a lot less time preparing the objects that you're going to image, the molecules you're going to image, and a lot more time processing a lot more data. So you just take many, many images. And the actual math of it, or the actual physics of it is the following. Sorry. So we're already having, let me see something happen. I think this was just on my end. Is it fine? Still on that side? Yeah, I can't hear because of the microphone, but you can see the slides well? Yeah, okay. Okay, so what you do is you grab a bunch of molecules, all of the same type, so you make a bunch of chemical copies, and then what you do is you freeze them. So you freeze them all in a thin layer of ice that's depicted here, and then you shoot electrons at it from above. Right? As you shoot electrons, some of the electrons get trapped in the molecule, and so what you see on the other side is some type of shadow of it. And now, of course, from just one shadow is quite hard to see what the molecule looks like. You're only getting it from an angle. Right? And worse even is that you have absolutely no control you have no way of telling the molecule how it should pose for this picture. So you get these projections, but you don't even know what was the rotation that the molecule was in. So this is quite a hard inverse problem, but on the other hand, this process is so cheap that you can easily get maybe like 500,000 or 1 million of these projections. So then the problem is you get maybe 500,000, 1 million such images, and you have to recover the molecules. Right? Now the images, in truth, they look a bit more like this. This is actually some images from a collaborator and from their lab. And you see, I can't even see that there's a molecule there. Just telling whether someone just gave you ice or they gave you ice with actual molecules that you're trying to image, even this problem is not so easy. But in the last, I don't know, maybe 40 years or maybe less, maybe 20, this has improved quite a lot. So I really like this image where you can see how the resolution of the molecules that we're reconstructing via this process looked like in 2013. Right? So you see here, it looks like a blob. It's still something, but it's quite a bit of a blob. And now with the new technology, you can get so much better. Right? You're starting to see this helix, like DNA type thing. You see a lot more. And in fact, this was just awarded the Nobel Prize in Chemistry, like 3 years ago now, for development. Now the development is, of course, both in preparation of samples in microscope, but also a lot algorithmically. The methods to process this type of data have improved a lot, and you can see it in how much better you can get these images. Okay? And so this is sort of one example that I keep in mind, and I'll show you a few others, and I'll try to convince you that these problems are actually quite related. Okay, so in a very broad sense, what I'm really interested in is understanding what are the limits of what one can learn from data. Right? Most people don't like being told what they can't do, but This is a big part of mathematics, right? Is you try to give lower bounds on what's possible to do. I want to know which methods work and why. And in particular, understanding why these new type of technologies working so well, like deep learning and related things. I think this, XKCD is usually so wise, and this is a great example of how wise the person making these comics is, where you see two people talking, one saying, oh, is this your machine learning system? And the other one says, yeah, you just put in the data, put some linear algebra and take answers out. And it's like, oh, how do you know if the answers are correct? You just, tune it enough until the answers look right. Right? This is actually not so different from what people do in practice, right? Of course, they don't just, how do they say it here? They don't just stir the pile. What they do is parameter tuning in all this linear algebra that goes into it. But there's a lot of, let's tune the parameters until the answers look right, and we don't quite understand why they're looking right, why these parameters are good. Are we seeing actually something true, or are we just seeing biases that we already had? This is extremely important in things like social privacy and social things where automatic systems will start deciding things that really affect people, maybe like which insurance claim should be paid out or not. And if things are not transparent, this can create very, very, very serious legal problems. And even in something that doesn't involve people, just the molecule example, you have sometimes this phenomena of what we call model bias, where because there's so much noise in this data, if the person developing the algorithm thinks that the molecule is supposed to look in a certain way, they will tune the parameters until the molecule on the other end looks exactly how they expect it. And from a scientific viewpoint, this is a huge danger. And there's many instances of literature of people claiming that what the other ones are doing is just this, what they call model bias, and sometimes Einstein from noise. So you see very heated arguments in places like science and the proceedings of National Academy of Sciences and so on and so forth. Right? And so another way of formulating what are limits of what one can learn is I want to understand what are the bottlenecks. What is it that makes learning hard or makes inference hard and so on? And another thing that it's maybe not studied as much, but I think is quite important, is understanding the limits to certifying that your answer is correct, or at least that your answer is not terribly wrong or in some quantitative way. And so I tried to look, as I was preparing a more broad audience talk, I tried to look at the history of of data science in a very broadly defined way. And I went to see, okay, when was the first time that someone started thinking about what were the limits of learning? If I wanted to estimate something, can I talk about the uncertainty that I have about estimating this parameter? How can I quantify this? So the first instances I found of this was the work of Bayes from Bayesian statistics, and Laplace, who sort of reinvented it. Then this shows up again a bit in the work of Lagrange and Gauss, the least squares and some primitive version of maximum likelihood. Then, of course, more modern things exist, like Fisher information, right? Fisher information is a way of quantifying how much a random variable or an observation of a random variable knows about a parameter that it depends on, right? How much data knows about the signal you want to learn, right? This has different languages in machine learning and signal processing and in statistics, but really the key concepts and the key questions are the same. And then I went to see, okay, what's the story of Fisher information? Should definitely have something to do with Fisher. I looked, it's not so simple. So people actually get quite heated on this, and I found actually many papers arguing about who came up with this way of understanding maximum likelihood and so on. And I realized that history is a lot harder than math. You see, I highlighted this box where you see lots and lots of familiar names, some saying that Fisher was the one responsible for everything, some saying that Edgeworth, maybe 20 years before, already had a lot of this. Edgeworth cites Carl Pearson, in this paper where he invents the moment of methods, because it's an amazing paper where he goes and studies a certain species of crabs, and he looks at the data of the length of maybe their claw, and he realizes that this is actually a mixture of Gaussians, and he does this all by hand. This paper from the 1890s is amazing. And so, but depending, history aside, by around the 1920s, people had a way of quantifying how much information about a parameter at a certain draw of a random variable had. Then, of course, there's even more sort of recent, more sophisticated things like the Neiman-Pearson lemma, which tells you what is the optimal statistical test to distinguish between two realities, right? If you don't actually want to learn, you don't care about learning a signal or a parameter or something, but there's two possible realities and you just want to know which one is the right one, then Neiman-Pearson characterized what are the limits of that, right? This is known as hypothesis testing in statistics. And then, right, Kramer-Raubaum make all the Fisher information stuff a lot more precise. And later on, there's things like minimax, contiguity, you know, lots of things even in machine learning and so on. And I quite like the notion of contiguity, so I thought I should mention it. This is quite a nice notion. Maybe I'll mention it again later. Now, of course, a lot of this also happened in information theory. Right? So in information theory, maybe around the late 40s and 50s, almost all of it in Bell Labs in the US, there's these two, we would call them mathematicians, maybe they would call themselves engineers, I'm not sure, but scientists. Claude Shannon and Richard Hamming, they basically invented information theory, you know, and the communication and channel coding and so on. Turns out, as I was preparing this, I actually spent quite a bit of time looking into history. Turns out they shared an office for a certain amount of time, and they never talked with each other apparently about these things, even though they both independently essentially discovered what we call today, I don't know, information theory, communication theory, or error correcting codes. So Claude Shannon in 1948 writes a paper called The Mathematical Theory of Communication, where he defines, among many other things, Shannon entropy. Right? So what this is, Shannon entropy is sort of the number of bits of information that are needed to identify a draw of a random variable. Right? So if you have a certain uncertainty, right, that you can represent by a random variable, right, reality can be one of these outcomes of a random variable, Shannon entropy tells you how many bits of information you would need to identify. Right? In the US, they call this the 20 questions game. Right? You have something you want to identify, and you get to ask 20 questions until you know, and see if you can tell what thing the other person's thinking about or something like this. Right? And actually, Claude Shannon then made this super. I learned too that Claude Shannon made this super sort of much more broad, and people read it a lot because Warren Weaver, which was the building I worked in I was working in last year, was named after Warren Weaver, rewrote Claude Shannon's paper in a way written for the engineers, and this had a huge impact. And then Richard Hamming, around the same time, so the story is that around 1947, he was preparing some big computation in Bell Labs, I don't know exactly for what, and he was using these old punch cards. This predates me, but I hear lots of stories about it, where he has some punches for ones and no punches for zero or something like this. And he puts this to code maybe on a Friday, and he comes back on Monday, and the whole thing had broken because one bit had flipped during the beginning of the process. Right, and so they had at the moment ways to correct for this, right? They had parity bits. So you put another bit counting the parity of the other one, so if it breaks one bit, you at least know it broke. Right? And actually, this was also pioneered by Tukey, who also worked with Shannon, was working also in Bell Labs and coined the name bit. And what Richard Hamming asked himself was, okay, since there's only ones and zeros, and I can have a parity bit that can tell me if there's an error, probably I can add a few more bits and not just tell if there was an error, but actually learn which one which one had the error. And indeed, he succeeded in doing this. This is his landmark paper from the 50s. And in this, he established what we know now as error correcting codes. So the two of them, what they did is they understood the following question. If I have some channel from which I want to send information, and this channel has some errors, has some noise. Interestingly, in the case of Shannon, he thought of this channel as being random. In the case of Hamming, he thought of it as sort of an adversary channel that could make the worst possible bit change. But what they asked was, if I want to send a certain amount of information through, how many more bits do I need to send so that the fact that the channel is noisy allows still on the other end to recover the information? And this was this was huge, not just for communication theory, but as we'll see later, this is actually how we prove a lot of our sort of statistical lower bounds with this idea. Because if we can argue that not enough information went through some process, then for sure the data will not know what was sent, what nature sent from the other end. And so this sort of really, really helps. Now, another point I want to make before I start talking about some real examples is that learning and estimation and this thing has different names in different places, is actually almost always boils down to an optimization problem. At the end of the day, you're always finding a parameter, a signal, or a model that best fits the data. And this best fits the data is clearly an optimization problem. Fit will be some type of, or minus some type of error, and you want to maximize fit or minimize error. And there's, of course, many, many classical examples of this, right? One of which is maybe maximum likelihood estimation. Even more recent ones, like the training, when people say they're training a neural network, what they're doing is they're finding the parameters for the neural network that best fits the data. This is just an optimization problem. And almost all the instances that I know of learning algorithms, once you decide what your model is, what your notion of fit is, you have to optimize it. Now, this raises, I think, a very crucial question, which, okay, the corresponding computational tasks of optimizing, are these easy? Are these feasible? I can actually do this on the computer. And so not all problems are easy, we believe at least. Many optimization computational problems are what we call NP hard. Right? This is a way of saying that the problem is difficult. One example is knapsack. Right? Knapsack problem is essentially the problem of, I give you a bunch of bags and a truck of a car, and I ask you, can you put all the bags in the car? Right? The optimization version could be, okay, can you put as many bags as possible in the car? But these are essentially the same question. Now, what makes this an NP, sort of NP complete problem, or an NP problem, is the fact that checking if the solution is good is very easy. If I pack the truck of the car for you and I ask you, okay, did I succeed? All you have to do is to try to close it. If it closes, yes, you succeeded. If not, then no. Right? So it's very easy to be checked, but very hard to be found. And so this is what an NP hard problem is. And optimization problems are of this type, because usually measuring fit is very easy. Right? I can always, it's just computing what the likelihood is, or what the error is, or something, but finding the best one is hard. And so I went also, as I was digging through history, I went to see when was the first time that these things seem to have been mentioned. And here is even more interesting. So there's this letter. This is sometimes called Gödel's lost letter. So in 1956, Gödel writes a letter to von Neumann, where essentially he asks, for the first time, as far as I understand, and maybe 10 years before anyone else asked, except maybe John Nash, I'll mention in a second, he asks von Neumann, okay, I have this computational problem. It was a knapsack, but you can think of something of this type. Could it be, what is the fastest possible algorithm to do this? Could it be that it takes linear time or quadratic? Right? Today, we really believe that the problem Gödel gave to von Neumann actually takes exponential time. Right? Unfortunately, this was maybe a year or two before von Neumann passed away. He was sick at the time, and so he didn't, at least as far as we know, he never replied to this letter. But it's amazing that this letter, maybe like 10, 15 years, maybe even before, has, one could argue the start of complexity theory. And interestingly, so in the US, the NSA disclosed maybe 5 or 10 years ago, a letter from John Nash sent him in 55, where it's a little different because John Nash seemed to be more interested in cryptography at the time, but he asks very similar types of questions. And given that all three of them are at Princeton, Turing had been in Princeton maybe, 15 years before this, even apparently talked a lot with von Neumann. It's clear that this type of questions were in the air there at least. But when this started being really, really made precise, was maybe 15 years after, in the work of Cook and Karp, and Dick Karp's 21 NP complete problem. So what Dick Karp did was he showed 21 popular problems, including like satisfiability and things like this. He showed them if one is hard, then all the others are hard, or if one is easy, then all the others are easy. And this class of problems is called NP complete problems, is what we think are the hard problems, right? And this is the famous NP versus P question. Okay. So now, if we think from the viewpoint of sort of the data analyst or the theoretical data scientist, the question is, should we be, if we're going to have optimization problems that are NP hard, we're maybe in trouble. So should we be designing models, statistical models, learning models, so that optimization is easy? Should we be modeling the world to start with in a way that we're sure is going to give us easy problems afterwards? And this has been the trend for a long, long time, right? I mean, in a way, linear regression is a type of, is a version of this. Maybe maybe computation is not the only reason, but convexity, right? Many times we model the world with convex things exactly because convex optimization is easy. Not because we believe that convex things better describe the world, at least most examples that I know of. And what I want to argue is that now we're really turning away from this. We're really believing that we should maybe model the world depending on how it actually wants to be modeled and deal with computation later. Or at least we should understand better what actual computations are hard and which ones are easy. And this is very much what my work is about. So let me now give you an example. Okay? So this is a problem I spent some time thinking about. So I'm now going to turn to a generative model of data. And the question is, when are we going to be able to learn the signal in this data? Okay, so here's the model. You're given two disjoint sets of n over 2 nodes each. Right? Think of n as a very big number. And now, so the nodes are, you should think of the nodes as, there's these n over 2 nodes, colored blue. There's these n over 2 nodes, colored red. Now, independently, you do the following. For every pair of nodes in the blue cluster, you connect them with probability P. For any pair of nodes in the red cluster, you color them with probability P. And any pair of nodes across, you color them with a slightly less probability Q. Right? So if Q is 0, then this is just two blobs not connected. If Q is the same as P, this graph, it doesn't matter which side it is in, right? And now, as clearly, the larger P is, the smallest Q is, the more sort of community structure this has. Did anyone raise their hands? I see something moving in the... No? Did someone raise their hands and ask a question? No. Okay, if anyone, just tell me on the mic. I thought I had seen something moving. Okay. But please, if anything is not clear, do ask. Okay, so now we have this random graph model. Now, what we do is we jumble the whole thing together, right? So now it's one big graph all jumbled up, and then I take away the colors, right? So before I had this sort of community structure, right? I put everything together. I mean, the community structure is still there. I'm just, moving the nodes around, and then I take away the colors, right? The community structure is still there. I'm just not given which community each node is at. And now the question is, can we recover the labels? Right? And there's been quite a bit of work on this, right? And so let me just show you sort of 3 theorems that we can prove about this. Right? So clearly, the bigger P is, the smaller Q is, the easier the question is, right? If P and Q is the same, for sure, this is impossible. Okay, so this is something we proved in 2014. This is sort of the statistical statement, right? Theorem is, turns out this is sort of the right way of scaling P and Q. Right, but this is just the right scaling for the problem to be interesting. Now in this scaling of log n over n, for the random graphs experts, they'll see why this is the right scaling. For us, it doesn't really matter. It's just the right scaling, and this is sort of the scale to look at things. Then what we can show is if square root alpha minus square root beta is bigger than square root 2, then the minimum bisection of the graph coincides with the true communities. Moreover, this is an if and only if. So if you're below this, if you're below square root 2, the problem is impossible. The minimum bisection, in this case, is the maximum likelihood estimator. We know that if it doesn't work, nothing else does in this particular case, right? It's the natural thing, is you split the graph in a way that it's even, because you knew originally it was even, and you try to cut in the middle as least amount of edges as possible. And so this means this is sort of the statistical threshold, right? Below this, it can't be done. Above this, if you just do minimum bisection, you can do it. Right? But now, I think minimum bisection was actually one of the original 21 card problems. This is a theorem definitely from the 70s, that minimum bisection is actually an NP-hard problem. Okay, so this means that statistically speaking, we know that once we're above this sort of level of signal, we can think of alpha minus beta as some type of amount of signal, what I call signal-to-noise ratio. Then minimum bisection works. However, minimum bisection is NP-hard. Right, so this doesn't seem terribly useful, because if it takes exponential time and I have an actual social network, I will never be able to run this. However, we proved between 2014 and 2015, that in this exact regime, so in the regime where we actually care about the statistics question, because we can solve it, or because it's possible to be solved, not only minimum bisection coincides with the true communities, but actually can be computed efficiently. Right, so this, the first time you see this is a bit strange. Right? We know that if you have enough signal, minimum bisection works. This is sort of the natural algorithm here. Minimum bisection is hard. However, if there is enough signal, it actually becomes easy. Right? Something in the graph makes it easy. Right? Because you should remember that NP-hard is a definition that depends on the worst possible instance. It's saying that there is no algorithm that works in all graphs. But we don't have just the worst possible graph, right? Nature is not our enemy. We have some generative model of data, and we just need our algorithm to work with that probability on that data. It doesn't need to work on some really weirdly constructed graph. And now the natural question, this is sort of what guides most of my research, is does this always happen? Could it be that from whatever reason we don't understand, statistical questions actually don't have computational hardness? I'll argue, unfortunately, this is not the case. So let me give you another example. Similar style of example. This is one I quite like. So this is called the hidden click problem. So the random graph model is a little different, but not super different. So I draw a graph, what we call a nerdy-Shreni G(n)1/2. So what this means is a graph on n nodes where each edge shows up with probability 1/2. Right? So all the edges have probability 1/2 of being there, 1/2 of not being there, and everything is independent. Okay? Now I'm going to draw another graph. The other graph is the same thing, but I'm going to add a k click. So I pick a number k, right? Like 100. And I'm going to pick k of these nodes at random of the graph. And now I'm going to add a click there. So what this means, I just connect all the edges in between. So now, I mean, the question that I want to answer is, are these two graphs different? There's many ways of asking this question. I can ask, can I do hypothesis testing between these two graphs? If I give you one of these graphs, can you tell which distribution it came from? Or I can ask, in the second one, can you find the click? Or I can even ask, on the first one, can you prove to me that there's no click there? Right? These are all sort of, they're not exactly equivalent, but they're morally equivalent, and what we know about them is the same. All right, so let's look at what we know. So, of course, the largest click on the one where I added the k click, provided k is big enough, will be k, right? There is a click of size k is what I added. It's not very hard to see, it's a union bound, basically, that the largest click in a nerdy-Shreni n(1/2) is of size 2 log n. Right? And so, in particular, from the statistics viewpoint, or information theory, or something of this type, we know that if k is bigger than 2 log n, for sure the two graphs are different. Right? All I have to do is compute the largest click. Right? Now, the largest click is something that's not easy to compute. It's also just as hard as the other things that I showed. But again, we can ask ourselves, are we in the same type of situation? So what we do know, and this already is over 20 years old, so from Nogalon and Benny Surakov was a colleague of mine here and a collaborator of them. In 1998, they showed that an efficient algorithm will work at finding the click or at distinguishing between the two distributions. This is roughly the same question, as long as k is bigger or equal than square root n. Right now, we know that if k is bigger or equal than 2 log n, the problem is possible. And they show that the problem is possible quickly with an efficient algorithm if k is bigger or equal than square root n. Okay? And the algorithm is essentially a spectral algorithm. You take the leading eigenvector of the adjacency matrix. You have to do very little more than that. And or you take an eigenvector of the adjacency matrix. Let me just put it that way. Okay. Now, since then, for 22 years, there's been no improvement, essentially. And in fact, this is believed to be hard. And is even used as a reduction primitive, in the sense that if this is hard, then you try to prove that something else is hard. Now, the way this is hard is different from the way that the problems were hard before. Right? Because here the claim is if k is smaller than square root of n, maybe n to the 1/4, then even though these are random instances, there's still no polynomial time algorithm that can distinguish these two graphs. Right? It's a very different type of statement. Right? And this I call the statistical-to-computational gap hypothesis. Okay? And this is sort of the most important take-home message from the talk, I think. Right? Is that in a lot of problems, and I'll show you a few more examples, and then depending on how much time we have, maybe I'll show a few on the board. That as you increase the signal-to-noise ratio, right, the size of the click, the strength of the communities, and so on, the problem becomes easier, not just statistically, but computationally. And in fact, in many problems, we see 3 regions. We see below a certain signal-to-noise ratio, right? This is below the 2 log n, and so on. The problem is just impossible, right? You just don't have enough data. You just don't have enough information. There's not enough signal strength, right? We know how to argue that something is below this statistical threshold since essentially even maybe the 30s, right? But certainly the 50s. Now, once the problem becomes possible, once there's enough information in the data, we sometimes see a region where, even though there's enough information in the data, there's some computational bottleneck in the sense that we cannot retrieve such information. It's sort of hidden from an observer that has access to only a limited amount of computation. And I'll try to describe a bit how we argue this. And then another threshold shows up, where we call the computational threshold, when the problem starts being easy, right? It's possible to do in polynomial time or even linear time, quadratic, and so on. Right? Now, for maybe the last 50 years, we've been focusing in trying to understand where the statistical threshold is. Right? I mean, if you go look at the papers, even like this the paper of Pearson about the crabs, or a lot of these papers from these times, they even do things by hand, right? It wouldn't even make sense to talk about, can this be done, can this statistical question be solved computationally or not, right? This is becoming crucial now because the amount of data that we're receiving is growing ridiculously. And so I would argue that going forward, it really is not very important when the statistical threshold is, unless in very specific problems. Because really what matters is when the computational threshold is. Because if something is hard, if something takes exponential time, we will not be able to do it in the computer with the size of data sets that we have now. Right? So a lot of my work is actually in trying to understand what is this transition. Since I cannot measure it in terms of information, we try to measure in terms of how visible information is, and so we have to come up with notions of that. So this is sort of what keeps me up at night, is trying to understand what is happening in this transition, how do we compute it. Okay. So let me try to give a very sort of broad stroke view of how do we do such things, and I'll show you a few different techniques, and then maybe I'll go deeper in one of them if we have time, but if not, I'm happy to also, if you're curious, write me, we can talk. I'm happy to describe all of this and answer any questions. So the question here is, what makes a problem hard? I would argue that maybe one thing that makes a problem hard is how complex, the complexity or the geometry of the set of solutions of the problem. Now, if you're a Bayesian statistician, maybe you can talk about the posterior distribution of the signal given the data, or the parameters given the data. Now it's the probability distribution, you can talk about its complexity. Right? Or maybe you take the space of solutions and you talk about this geometry. Right? What is its topology? Like, is it connected? It's not connected. Does this matter from the computational viewpoint, and so on? So I'll try to give two examples of the two sort of views of this. So let's go back to the stochastic block model, right? To this model where we had the blue nodes and the red nodes and so on. Now let's think like a Bayesian statistician, right? You know how I drew the graph. So you know all the forward probability, so you can compute, posteriors. Well, maybe not efficiently, but you can definitely talk about them and compute them if you have enough time. So let's just think about them. So let's see, we see the graph. And now we see the graph, and we want to ask about the probability distribution of the labels given the graph. Right? If we understand this, we understand everything. Right? Not only this, it tells us what's the most likely community structure, but it even measures uncertainty, tells us which one is the second most likely, and so on and so forth. Now, if you think about what this probability distribution is, if you think of the labels as plus or minus ones, this is a distribution over the hypercube. For each one of these nodes, there's a plus or minus one. There's a possible spin. So this type of probability distributions where you have a bunch of particles that can be up or down and have spins, and their spins interact in strange ways, like how a posterior interacts with, like, marginals of posteriors interact. This is exactly what is studied in statistical physics under the name of spin glasses. Right? This is how, Curie-Weiss, the Curie-Weiss model explains why if you have a bar of iron and you heat it up too much, it all of a sudden stops being magnetic. Right? This is explained exactly by putting a model on where each of the atoms is up or down, and there's a certain distribution, and as temperature grows, something happens. Right? And so it turns out that you can use a lot of these tools of spin glass, the same way that what they do in physics is they try to understand phase transitions. Right? Like, thing goes from liquid to gas, or something goes from magnetic to non-magnetic, or something like this. Turns out we can use these tools very effectively to make predictions about phase transitions on this probability that seem to match exactly with when the problem is hard or easy. So you go into the physics, you grab tools that they've been developing for maybe like 30, 40 years, and then you use those to try to describe when are the phase transitions that happen in sort of this this model of distributions over node spins, right? So you think of this as some kind of, fake physical system. And the predictions that you get of when the phase transition should happen match exactly where algorithms stop working. And in fact, for these examples, we've been able to prove not that algorithms don't work, but at least that this view is equivalent to many others, right? So we really believe that there's something about the phase transition in this type of tools to understand phase transition physics that's saying something about computation. We don't quite understand what, but I think we're starting to very slowly. Now, here's another example. Let's take the graph now, the G(n)1/2, right? So the graph where every node gets connected with probability half, right? So this random graph. Now I can ask, what's the geometry of the cliques of size bigger than omega, right? So you fix omega, 10, and now I look, give me all possible set of 10 nodes that are all connected in the graph, right? This will, of course, be a random set, but by concentration of measure, its property should have some limit. And now you ask, what's the geometry of this set? And it turns out by studying this, you can actually get a lot of information about the hardness of finding cliques. And so let me give you examples of things that you can predict, some of which we can prove. I mean, it's very difficult to prove that something can't be done computationally, but you at least prove that it's equivalent to other things or that it can be done statistically. So using sort of the first analogy that I'm describing, you can show that the community detection problem, the same one I described, in a slightly different goal of what's called weak recovery, but for the sake of this talk, that's not important, that this actually has a computational gap if the number of communities is bigger or equal than 5. So if instead of 2 you have 5, and the same P and Q, there are 2 phases. There's a phase where there's nothing to learn in the problem. There's a phase in which if you could do not minimum bisection, but minimum 5 cuts, you could solve it, but you cannot in polynomial time, we believe. And then there's the phase where you start being able to do it efficiently. Now, if you study the geometry of cliques, the largest clique is of size 2 log n. But if you now study the geometry of cliques, you see something really interesting, that cliques seem to be, the set of cliques seems to be sort of, think of it as a big ball, at least connected, up to when the cliques are around size log n. But if you ask for cliques of size 1.1 log n, their geometry seems to change a lot, or at least this is what we believe. And in fact, with this, you can make a very strong argument that finding cliques of size 1 plus epsilon log n for any epsilon is hard. And in fact, we don't know any way of doing it. Finding a clique of size log n is very easy. We know cliques of size 2 log n exist. We have no idea how to find efficiently cliques of size 1 plus epsilon log n. And if you look at the geometry of the set of cliques, it really changes. There's something drastic that happens that we believe is the cause for hardness. And in 2013, in a very similar problem, David Gamarnik and Madhusudan basically proved that at least an algorithm that only makes local decisions could not succeed at the problem that's essentially the same as this. Now, I myself have worked in quite a few of these questions. In particular, I've been very interested in understanding the hardness of doing principal component analysis when you believe there is some structure in the low rank structure that you're trying to find. So the low rank signal that you're trying to find has some special structure, right? So a good way of modeling this is with random matrix spike models, and we have shown using exactly these types of tools, or argued that there's actually huge computational gaps essentially in most structured principal component analysis problems. And I'll describe one a bit later in the talk. Now, there's another sort of, there's many heuristics to try to predict hardness. There's another that should be mentioned, which is sum of squares. So sum of squares is a hierarchy of algorithms, right? They're sort of inspired in a certain way on Hilbert's Nussdalen-Satz. I will not say much about this, but they're a way of, their algorithmization of a version of Hilbert's Nussdalen-Satz that works over the reals. Right? It dates back to Pablo Perillo and Jean-Bernard Lasserre in the beginning of the 2000s. And this hierarchy is a hierarchy of algorithms that get ever better, but also ever more costly. So if you believe it's optimal in some sense, you can now ask, okay, for my problem, how far do I need to go in the hierarchy? And if I can answer that question, if I think it's optimal, I see how much the algorithm costs at that level of the hierarchy, and I can make a prediction of how much the best algorithm costs. And this actually works, surprisingly well. Another maybe simpler idea is that's due to, maybe it was, not explicitly said in a few other papers in the community of theoretical computer science, but the first people who explicitly described this was Sam Hopkins and David Storer. And the idea is a bit different. You ask, what if my estimation or my statistical test or something needs to be a low-degree polynomial of the data? So you restrict yourself to low-degree polynomials of the data, and you ask what you can do. And turns out this is this amazing way of making predictions of computational hardness that we've been exploiting a lot. So we can prove things like this. For sparse principal component analysis, so when you're doing PCA, principal component analysis, finding low-rank structures in data, if you want to exploit sparsity, you believe your low-rank structure has sparsity. Maybe you're doing something in genetics and you think that the effect should depend on just a few genes. Then if you want to exploit sparsity rho n, you have to, we believe we have evidence, or say rigorous mathematical evidence, we can't prove hardness, but we can base it in other conjectures, that the required computation for this is sub-exponential. So it's exponential of rho square n. So if your sparsity is, say, root n, or one, say rho is 1 over n to the 1/4, so you have n to the 3/4 sparsity, then here you get the exponential of n to the 1/4, right? But the point is that for a level of sparsity, we can make a precise prediction of the computational cost. And the prediction is, if we're trying to understand how well do these heuristics predict hardness, we make an extremely precise prediction, and we have an algorithm that works essentially exactly until then, and no algorithm that can pass it. And so this seems to be the exact computational hardness of this, this statistical question problem. Now, there's another thing that I've been, I spend a long time thinking about this. It's a bit harder to motivate without talking more about statistical physics, but there's something in statistical physics called the Sherton-Kirkpatrick model. If you're an optimizer, maybe the best way to think about it is you're given, it's completely equivalent, you're given a Wigner matrix, so a matrix n by n with all the entries are Gaussian, you just ask for it to be symmetric. And now you just ask yourself, can I solve the quadratic optimization problem on it over the hypercube? Right, so I take maximization of x transpose wx, where x is plus or minus 1. Right, this is for sure an NP-hard problem, but now I ask you, can you solve it? W is Gaussian, is not worst case. Can you solve this problem? And we now believe that actually arbitrarily good solutions can be obtained, but we proved, based again on a conjecture, that certifying a non-trivial upper bound for this is hard. So you may actually be able to get arbitrarily good solutions, but for you to be sure that you actually got an arbitrarily good solution, there's a significant computational hardness in this. And this comes motivated from statistical physics. I would need more time to describe exactly what it is. So now I'll go back a little to cryo-electron microscopy to say what we can, using these tools and others, what we can say about cryo-electron microscopy just in the last few minutes. So turns out using a connection between the statistics of cryo-electron microscopy and algebraic invariant theory. So this might sound crazy at first, but what we realize as we're studying the mathematics of Cryo-EM is that the fact that the molecules get acted by rotation, right? There's an element of SO3 acting on them. Because of this, there's actually a lot of algebraic structure that is left in the problem that you can exploit. And so taking advantage of that algebraic structure, we actually proved that it is impossible to get, we can understand what are the lower bounds of how many images are needed to get a certain quality of reconstruction. And this depends on the algebra of invariant polynomials with respect to that action. Okay? So you ask a certain question about this algebra of invariant polynomials that is invariant with respect to this SO3 action that's acting on the molecules. And once you answer that question, which is turns out to be a simple, not so hard question in this case, then you can tell that the optimal reconstruction quality is square root of the number of samples. This is typical, it's usually how it is, times the signal to noise ratio of the data to the cubed. And this is a very weird thing. I don't know of any of other problems that have this. So in the case when the signal to noise ratio is very low, there's this cubic effect that's very strange, right? It means that if your data is a signal to noise ratio that's half, then you actually need 8 times more, or 2 to the 6 times more more samples, right? This effect, usually you get an SNR factor, right? The number of samples depends on SNR square, not on SNR to the 6. So we're very surprised by this. And in this case, there's no computational gap. We have algorithms that can match this. However, in real Cryo-EM, you know, in the practitioners that actually want to use this, they want to use this on a soup of molecules that are sort of in the natural environment, in particular in proteins. And they don't want to, you know, have to treat them in ways, because when you sort of take them out of the natural environment, they might change. And in particular, and sort of when they're close to their environment, sometimes they have many conformations, right? So here's an example. I think this is a ribosome, where you see that there's 2 conformations it can have. Maybe it's like on or off or ready to bind to something or not. And this is actually extremely important to understand this conformation. And now, if you have exactly the same version of the Cryo-EM problem with these heterogeneity, what we call the heterogeneity problem, so with different conformations, here we can actually argue, using roughly the same tools, that there is a computational gap. So as soon as you introduce more conformations to the molecule, which is actually what people want to do in practice, there is a computational gap that arises. And the cool thing, you know, I was quite happy with this, is that when we saw this really confusing dependency on SNR cubed, and then we were talking with our colleagues, and Fred Zigworth, who's a professor in the medical school in Yale, said, oh, I had seen this before. And so he pointed us to his paper from over 20 years ago, where he does some experiments on the quality of the reconstruction, right? So you see here quality of reconstruction and the quality of the data. And he makes this comment in his paper that something very strange happens, that when you have low SNR, the dependency on the SNR is cubic, right? There's a log-log plot. So the exponent, you see it on the slope. Right, and he has this comment about how he doesn't understand why this is happening and so on, but he does see it and he does observe it, and so we're able to explain this. We also learned that, you know, practitioners know things way before you could ever. If you think you learned something new, the practitioners already knew it. Maybe not 20 years ago, but a certain number of years ago for sure. And so let me just tell you about other methods very briefly of showing hardness. Right, one thing one can do is the traditional computational hardness. The view of hardness, which is reductions, right? If you believe that we cannot do hidden click beyond a certain level, then we also cannot do sparse PCA beyond a certain level. So there is some success in this, very limited. Maybe the best example is the work of Quentin Berthet and Philippe Rigolet, where they show that if hidden click is hard, then sparse PCA has a certain hardness too. Another thing I've been doing a lot more of now is in trying to understand the geometry of random optimization landscape. So let's say, for example, you have a random multidimensional polynomial, say of cubic polynomial. And now you, high dimensions, and you take the coefficients to be Gaussians, for example. Now you can ask questions of the type, how many local minima does this function have? Let's say you consider it just on the sphere, right, just to normalize. And now you can ask, how many local minima does it have? How many critical points whose saddle has index 1? Right? You can ask all sorts of these questions. And actually, there's work that dates back quite a few years from doing this in random geometry. Right? Especially if the function is Gaussian, something called the Katz-Price formula can tell you a lot about the average number of critical points, about complexity of the landscape in this way. So we've been doing a lot of these calculations to see if they help us understand hardness of optimization on random problems. There's another models in statistics, such as statistical query models, where you restrict what you see. There's also something very, maybe like a year ago, me and a few collaborators and students ran an experiment where we tried to, because deep learning seems to learn everything. You can ask deep learning. I mean, it makes more sense to ask these graph neural networks, but the idea is very similar. It's like deep learning on a graph. And you ask it to learn to, say, solve the travel salesman problem. Right? So we actually did this. We gave it lots and lots of instances of the travel salesman problem. And you can either give them solutions or you can let it evaluate the attempt it makes by some type of reinforcement learning. I don't want to get much into that. Or you give it, say, instances of the stochastic block model, graphs, and you ask, find the community. Right? And you give it, I don't know, millions of such examples, and you ask it to learn an algorithm. And it learns an algorithm. And amazingly, it does quite well in traveling salesman, for example. But in particular, in the stochastic block model, where I know exactly where the limits are, it does quite well. It essentially gets to the limit. So I'm quite interested in understanding whether, by knowing these limits and understanding exactly the statistical problems, and the fact that these neural networks are able to solve them, if I can, one, understand better the neural networks, and two, actually use them to predict when problems start being easy or hard. And of course, understanding why is it that they're learning these algorithms. Right? We have some very preliminary work on this, but I don't have time to describe. And of course, as a mathematician, the question that really drives me is, I think we're really far from being able to prove that things are hard, right? We haven't been able to prove that P is different than P for many, many years now. Right? Even though, if you read a paper from like the 80s, from theoretical computer science or complexity theorists, I've read papers where in the introduction, they almost apologize for not having yet proved that P is different than P. As if sort of the community in the 80s was embarrassed that they have not proved that. But 40 years after, we still have no idea how to do this. So proving that computation is hard, seems very difficult. But at least, as a mathematician, the natural question is, I have all these heuristics, they seem to predict the same, can I at least prove that they're equivalent? And yeah, we can prove that some of them are related to the others, but we don't quite have a universal story yet. And looking ahead, this is more repeating what I've just said, but I really want to understand what makes problems hard. How do we find the computational thresholds? Like what makes the problem hard? What changes in this threshold? Are all these methods actually equivalent? Like, we have some suspicion that actually a lot of them are seeing similar things about the data, but we can't quite put our finger on what yet. I'm also very interested in what can be certified, and in particular, what random properties are acquired. It's what I call a hidden rare event. So if I give you, say, a random graph, its largest clique will be of size 2 log n. But if for whatever reason a very rare event happened and its largest clique is of size 3 log n, this would be extremely rare. But I believe this is what I call a hidden rare event, or a quiet rare event, in which even though this is a rare event, a very, very rare event, there is no way for me to be sure that it didn't happen, at least not in polynomial time. And so I've been very interested in understanding such rare events and what makes them hidden. And we have a big suspicion that what makes them hidden is that essentially they don't affect the low order moments of the data. Right? I mean, I can say a bit more of this if someone is interested. And of course, I always pick the Gaussian model or the graph and so on, but the very natural question is there a universality phenomena going on? I think we're starting, at least we can move from Gaussians to Bernoulli examples. So I guess we're starting to make baby steps on this, but we're really very far from having a real universality phenomena in the sense that random matrix theory has developed in the last few years or in the last decades. And of course, I mean, this is all a house of cards, right? It could be that 10 years down the road, 100 years down the road, someone comes up with an algorithm that actually refutes all of this and just is able to solve everything. So, what would such an algorithm look like? And is there any hope that such a thing exists? And as I mentioned already a bit, can this actually explain or help explain why learning is working so well now, deep learning neural networks? By trying them out on these problems that we really understand what's going on, can we get a better picture of what they're doing, why they're doing it? Can we understand if there's computational hardness related to generalization, right, in machine learning and so on? Okay, I'm already a minute over time, so obrigado, thanks. And yeah, I'm very happy to take questions. I guess it ended up being timed perfectly for me not to present anything on the board, but maybe if there's any questions, I can answer it there. All right, thanks so much. I hope it was clear, and yeah, you could follow and understand everything.
Questions?
So maybe I'll stop sharing the slides now so that I can see the room better.